Press.
Sure. Comes on everyone. Last thing that we're doing was calculation of angular momentum. Sure. Other scams on. We have a particle of mass m projected with event theta. You can take this point as origin. Find angular momentum of the particle about the origin as function of time t. About the origin at h max and at time t. Two different questions. Let's get this. Hmm. So how do we do this? H max was fine. So when you're at h max, what is the speed? U cos theta. Extend the velocity vector. This is your origin. Drop the perpendicular. The perpendicular distance is h max. So angular momentum will be m into u cos theta into h max. The direction will be minus k cap. You know h max ka value. U square sin square theta by 2g. Check. But what about function of time t? That I'm more keen on. But there are two ways you can handle this. One, we can use a vector form. Angular momentum is equal to mr bar cross v bar. And I hope you're Homer from kinematics. What is r bar? U cos theta I cap. U sin theta t. Minus half gt square j cap. U cos theta I cap and U sin theta minus gt j cap. Then you have to do r cross v bar there. Check it out. This is one way. Srihari, then give me the final answer, right? So you have to do cross product. Yeah, it's lengthy, but you will get it. So this would be MR cross V bar. So U cos theta T I cap and this thing that will be gone. So that will be U cos theta T. U sin theta minus GT. I cross J will be K cap plus. That will be J cross I. That will be minus K cap. So that will be U square. U cos theta sin theta. U cos theta sin theta, that is cancelled. That would be U cos theta GT square, and this will be U cos theta GT square by 2 minus. You end up with, there is an M also. We get mg U cos theta T square by 2 minus K cap. That's your answer. Getting it? But like there's a faster way to do this. See. As this is moving at any instant, the vector is mg. If you drop the perpendicular, this distance will be U cos theta T. So torque will be mg U cos theta T minus K cap. This is your torque. And we know torque is nothing but dl by dt. So integral dl bar will be mg U cos theta integral T dt minus K cap. This will be 0 because you're initially passing through the origin. L bar, this will be 0 to T. Mg U cos theta T square by 2 minus K cap. Check. Is this clear, everyone? Any doubts on this? Let's see the next one. Again, if you see, we're still playing with the calculation of angular momentum. So we have a particle M here. It's going in a circle, conical pendulum. This is O dash, the point of suspension. This O is the center of the circle. This is a string of length L. This angle is theta. This is going with speed u. Find the angular momentum about O and angular momentum about O dash. This is your conical pendulum. O is the center of the circle and O dash is the point of suspension. How do we do this? Let's see. Look at the first one. Angular momentum about O. So O is your center. So at any instant, if you take the velocity here, this would be your r bar. This would be your velocity vector. This is your r bar. This is your velocity vector. Maybe I'll take some other point here. This is r bar. This is your velocity vector. Velocity vector and r bar. So if you see r cross v bar, you will find the angular momentum is in the vertical direction. This is your L bar. Right hand thumb rule. M r cross v, right? Actually, it is in the reverse direction. Take it out. M r cross v will be in the downward direction. And what about the radius of this circle? This is L. This is theta. This is your radius with L sine theta. So therefore, the angular momentum will be M r. R is L sine theta. The speed is u, and the direction is downward. I'll just leave it like this. It depends. Matlab, you can take something as I cap, j cap, anything. It will be pointing downward. And if you see, this is constant. Right? Maybe I can choose this thing as x, this thing as y, and maybe this thing as z. And this will be minus k cap. Is that clear, everyone? So this is an angular momentum about the center, and this is constant. The magnitude is constant and the direction is constant. And if the angular momentum is constant, then the torque must be zero, and that kind of makes sense. What are the forces? Mg, tension, theta, t cos theta, and t sin theta. This is your O dash, O. So here t cos theta and mg will cancel, and t sin theta passes through the passes through. Therefore, torque about the center is zero. Therefore, angular momentum is constant. I hope you remember torque is dl by dt. If your angular momentum is constant, the torque of the system must be zero. So if you're taking torque about the center, there is no torque. The angular momentum remains constant. Is this clear, everyone? You can get some really good theoretical questions on this. So we will be discussing in more detail. In the second case, you get something else. You take L about O dash. This is your O dash. What is R vector now? Your R bar is this thing, the length of the string. That is a direct thing, R bar there, right? And this is your velocity vector. So if I try to show you this, at any instant, you have R bar like this, and you have velocity V bar like this. So if you take R cross V bar, I think I should have taken velocity this way. Your life would have been little easy to see at least. Let me take velocity this way. Nothing, it just makes things look more clear. At least for me, at least to draw, it will be easy for me. This will be L bar, this will be L bar, this will be L bar. It will be out of the plane and this will be plus k cap. Clear? It's the same thing. I'm just making it more neat, nothing much. Now here, velocity would be this way. This would be R bar, this would be V bar, this would be R bar, this is your V bar. So when you do L cross B bar, you can see this angular momentum, right, will look like this. It's coming out of the plane, meaning the vectors will look like this, like a crown. Huh? This is how your L bar will be. Are you able to visualize how that vector looks? The L bar vectors will be like a crown. Clear with this. Now, if you look at the magnitude is constant. This is a perpendicular there. So L about O will be MUL. That's your magnitude. But the direction is changing continuously. Yeah, we can get that also in terms of I cap, J cap, but okay. But the main idea is this, the direction changes. So L about O dash is not constant. Can you see it's the same thing? About one point it is constant, about one point it is not constant. So we can actually resolve this into two components here. You can say there is one vector which is L perpendicular and then one vector L parallel component. The L perpendicular is constant, whereas the L parallel vector is rotating. Is that making sense? So your L parallel is rotating in a circle, whereas the L perpendicular is in the constant direction. So if torque is not constant, that means there must be a torque. But everyone clear with this? That would be a straightforward question. What is the angular momentum about O dash? Is it constant? It is not constant. Is the magnitude constant? S magnitude is constant. Any doubts on this? Then, now let's see why, if it is not constant, that means there must be a torque. Where are you getting this torque from? Now, if you look at the vectors there again, I think let me draw this thing. If you take the forces, this is O dash. What are the forces? Mg, and this is the tension. Tension is passing through O, but there's a torque about Mg. Torque due to Mg is not zero. Torque about O dash will be Mg into L sine theta. And this is perpendicular to this plane. This is O, and let's call this thing some P. Perpendicular to O dash, OP plane. So let me show the whole picture of how it looks. This is your O dash. This is your R bar. This is your velocity. The L bar will be perpendicular to both of them. This is your L bar. And you know how is the torque? The torque is this way. The torque is tangential to velocity actually. This is the torque direction. So as this vector is rotating, if you see the torque is also rotating. Look at this thing. The torque is always coming out of the plane, isn't it? Here in this case, mg is this. It is rotating this way. If you look at the torque direction, the torque is coming out of the plane. As this vector rotates, this is R bar, this is V bar, this is L bar, and this will be torque again. You can clearly see here the torque about O dash is always perpendicular to angular momentum about O dash. Both the vectors are perpendicular. Clear this? Now, we have seen something like this before, in some chapters, circular motion. If you remember this discussion, if F bar is perpendicular to V bar in a circular motion, what happens to the speed? The speed remains constant, but velocity changes direction. Same way, we can also argue here, if torque is perpendicular to L, the magnitude of L naught bar remains constant, but the direction changes. Because it is perpendicular, it cannot change the magnitude, but it will keep changing the direction. Okay. So if the torque is perpendicular to angular momentum, the direction will change, but the magnitude cannot change. Are you getting this? Can you see O and O dash, the game completely changed. Torque about O was constant, torque angular momentum about O was constant, torque was zero. But when you take torque about O dash, magnitude was constant, but direction is changing. That means there is a torque, but this torque is not changing the magnitude, but is only changing the direction. And that is possible because torque is always perpendicular to L bar. Now, the easiest way to understand this is to see this in terms of force and velocity. It will be more easy to compare that instead of directly seeing torque and angular momentum. Are you clear with this? Is this clear, everyone? Any doubts on this? Arya? Clear. Now, how they'll frame a question in the exam? Huh? This was a question in the JEE exam. Yeah, there's no doubt, but keep your cam on, God. Torque is given by A cross L bar. Where A bar is a constant vector. This thing came in the exam. More than one choice question. L bar is your angular momentum, tau is torque. The options were like this. L bar is constant. Mod L bar is constant. Component of L bar along A bar is constant. L bar is variable. It's the four options. Arya, remember last time you were asking, na, sir, how is the torque direction and all? This was the thing. So how will you solve this thing? So this was actually the question which I taught you right now. It is the same thing, but it was asked in a different way. Which of the following four options are right? Get that. A is a vector. Array, how can you do a cross product between a scalar and a vector? Right? Now look at this question, okay? First thing, what did you say? Torque is equal to A cross L bar. We know in a cross product, if you do A cross B bar is perpendicular to both A bar and B bar. The torque is perpendicular to A bar and torque is also perpendicular to L bar. That is the first thing. Right? And we also know torque is nothing but dL by dt. That means if you apply torque, angular momentum must change. But if torque is perpendicular, the magnitude cannot change. Since torque is perpendicular to L bar, magnitude remains constant. And whenever you think, okay, why is that exactly happening? Think about the uniform circular motion. That is the best way to, think of it, like easy to visualize. Rotational motions are a little difficult to visualize, but translation motion you'll understand. If force is perpendicular to V bar, mod V is constant. Velocity changes because of direction, but not magnitude. Right? And now since torque is perpendicular to A bar, that means there is no component of torque along A bar. Therefore, angular momentum along A bar will not change. If there is no torque in a particular direction, then in that direction, angular momentum cannot change. So component of L bar along A must remain constant. Think of like this. If there is no force in x direction, then velocity in x direction cannot change. Is that clear, everyone? So from these options, magnitude is constant, component of L along A bar is constant, L bar is variable, BCD. Is that clear, everyone? Arya.
Sir, can you please show the solution? I have a doubt in it. Sir, in this, the third statement which you wrote, I visualize two vectors which are like this forming an acute angle, but their cross product can be this, right?
ये है ना basically ऐसे assume करो ना यहाँ पे what is that vector mg is your a bar,
Okay.
right, and l bar is one vector.
Hmm.
करेंगे so
Yes.
a cross l bar, so we have to get a vector इसमें not l bar, not the full l bar, ये vector था. There's an l perpendicular and mg ना.
Yes.
So if you take this mg here, look at this thing. So this mg and this l perpendicular, these two are perpendicular. This is changing, l perpendicular is changing. This
Okay.
l parallel is changing and l perpendicular is not changing.
Yes.
No, so how are you assuming?
Sir, I visualize like two vectors to be forming acute angles and like a
नहीं ना,
contradiction
इस
of
केस
what
में
you
देखो
said,
ना,
right?
ये तो एक्चुअली ऑब्ट्यूस होना चाहिए ये.
Sir, but they give the total angular momentum over the point, right? in the
फर्क
question.
नहीं पड़ेगा actually. Total angular momentum about the point is L bar that is changing in magnitude. Contradiction क्या exactly?
सर अगर आप बोल रहे हो कि टॉर्क इज परपेंडिकुलर टू ए बार एंड टॉर्क इज परपेंडिकुलर टू एल बार, तो
ठीक है. A bar and L bar, let's say they're in one plane. वो तो है ना, two vectors will become in a plane.
ओके आई गेट इट.
ना? Not lines, vectors can be always moved into a plane. All clear with this question? Getting it? This might look like a very simple question. If I just asked you angular momentum of O and O dash, it would have been done. But you can see the kind of discussion we did. O is simple. O dash is a plane. The direction is changing. The vector is rotating. The L bar is not constant. It is continuously rotating. You know where else you see these kind of things? Did you ever see a top rotating? When you see a top rotating, the top is rotating like this. So this is an angular momentum ka vector. But the top itself is going in another circle, isn't it? So the L bar is also rotating. We call that thing precision. Ever heard about that? If you look at Earth ka rotation, right? We say na Earth is rotating about some 23.5 degrees ka axis. But this Earth ka axis itself is rotating in another circle. That's the precision there. So that happens every few thousands of years. So whenever that thing goes to the other thing, we get an ice age. I think the last ice age ended in 20,000 years back. Next one will come another 15, 10,000 years ke baad mein. So we are kind of safe. We just have to buy a good sweater. So next thing. We have a rod here, mass m, length l. Here we have an insect, mass m. So this insect is going with speed u. And it is observed for some reason this rod omega is constant. Gravity is there. So normally speaking, because of gravity, the rod should go faster and faster. But we notice as the rod is rotating, as this insect is walking, let's say at a distance x, the omega still remains constant. An ant walks along a rotating rod with speed u. We observe the angular velocity of the rod remains constant. Not only think about that, if you leave a rod like that, there will be an angular acceleration and the rod should accelerate. Find u in terms of, find the speed of that ant in terms of u and theta. In terms of x and theta, where x is the distance from the hinge and theta is the angle rotated by the body. Are you getting my question? Normally, if you keep a rod legs and leave it, won't it go faster and faster? But something is happening. Once the ant started walking on this, for some reason, the speed is not changing. Find the speed of the ant as function of x and theta, where x is the distance from the hinge and theta is the angle rotated. Let's see how will you handle this. Then now slowly from calculation of angular momentum, we are entering into torque and angular momentum relations and so on. Forget about solving the question. First, think like why it is happening, and then we can go from there. Anyone figure it out why it is not changing? See what is happening. When this ant is moving here, if you draw the FBD, we have your own mg, rod ka, we have ant ka mg. This distance will be L by 2 cos theta, the perpendicular distance. And this will be x cos theta, the perpendicular distance. So if you take the torque about the hinge, that will be mg L by 2 cos theta plus mg x cos theta. So we know the torque. Now, if you take I about the system, we have moment of inertia of the rod, which is ml square by 3 plus mx square. You're getting the problem there? I is not constant. If I is not constant, then you can't use torque is equal to I alpha. The formula is actually I d omega by dt plus omega di by dt. Now, people will think, okay, omega is constant, so alpha is 0, so torque is 0, but torque is not 0. So here, omega is constant, so this term is 0. So torque here will be mg L by 2 mg x cos theta must be equal to omega. Differentiate this di by dt, that will be m 2x dx by dt. And remember, x is this distance, so the rate of change of x will be the speed of the insect along the rod. So this would be ml by 2 plus m x g cos theta 2mx omega, that will be u. They're done. You'll get it. Not a great answer, but so this is what was happening. The insect is walking in such a way the rate of change of moment of inertia balances the torque thing. Got the idea? So this is a variable moment of inertia problem. So that is how you can mess up moment of inertia. Any doubts on this? All clear? Go ahead. Next one. Let's say we have a solid sphere rotating with omega. Due to internal forces, it shrinks to half the radius. Generally happens with stars. At the end of their life cycle, right, the stars will just explode and they also implode, and the whole planet, the whole star shrinks due to internal forces. And if the force is strong enough, right, they create a neutron star. Due to internal forces, it shrinks to half the radius. And this becomes small. Mass is remaining same. M and R by 2. Standard question. And angular velocity changes. Find the new omega and change in kinetic energy. This is a standard question. Meaning pretty standard. Like CET ka, it's a straightforward question. Keeps coming in some other exam. Get both. Find the change in angular velocity and change in kinetic energy. There, now we are entering conservations. Did you see the wordings of the question? This is something I told you, remember? Look at the wording of the question. I don't care what is happening in the middle or how did it shrink. I'm only interested in the final velocity. So where do you hear this kind of words? Find a final velocity, final position, final. Conservations, isn't it? And there are three conservations: energy, linear momentum, and angular momentum. Here, does it make sense in energy? Internal forces can do work, right? So maybe energy is not conserved. Linear momentum, nothing is moving only linearly. The only thing left is angular momentum. Since there are no external forces, the torque will be zero. Therefore, initial angular momentum is equal to final angular momentum. There, we started with conservation of angular momentums now. Again, we'll start with simple ones and then we'll slowly bump up the level for conservation. Minus 3 mr square omega square by 5. Okay, let's see. Hmm, 4 omega. It's see. Since torque due to external is zero, L bar is constant. I1 omega 1 is equal to I2 omega 2. So initial angular momentum will be 2 by 5 mr square omega. This will be 2 by 5. Mass remains same. Radius becomes r by 2 whole square omega nu. Omega nu will be 4 omega. It becomes 4 times faster. Similarly, when you talk about energy, kinetic energy is half I omega square, multiply and divide by I. This becomes I omega whole square by 2y. So this can be written as angular momentum square by 2y. If you guys see this thing kind of looks like kinetic energy is equal to momentum square by 2m. Can you see the resemblance? So you can clearly see the formula here. So change in kinetic energy is L square by 2I final minus L square by 2y initial. You can substitute and finish it off. Or you can just substitute half Li square and you solve half I omega square. It works. But you can clearly see when the ball shrinks, moment of inertia will decrease. Therefore, the final energy is more than initial energy. So the ball actually gains energy. That comes from your internal work done. So work done, change in kinetic energy must be positive. Okay, people got some value for this, which is 3 mr square omega square by 5 it seems. Check. Check your signs. Is that clear, everyone? Any doubts on the steps? No. They can ask some theoretical questions also, okay? Tell me one thing. Let's say if all the ice on the earth melts at the poles. So let's say due to global warming, all this ice at the poles melts. What happens to the time period of the day, duration of the day? If all the ice at poles melt, what happens to the duration of the day? 24 hours. Now, will it be more than 24? Less than 24? Same as 24. What happens to the duration of one day? Increase, decrease, remain same. What do you guys think? Will the day be longer or smaller? Will you need to go to your classes more or less? Let's see. I know 1 day is 1 day only in terms of hours. So what is happening here? Now, if all the ice melts here, what happens exactly? The the whole thing will get distributed as water. So all the ice here, once it melts, the water will spread out here. So even though the mass is same, the moment of inertia increases, the mass is increased. I increases and L is equal to I omega is constant. Therefore, omega decreases. So Earth will actually rotate slower. And we know time period is 2 pi by omega. So it will take more time to complete one rotation. So basically, the time taken for one rotation is called 1 day, basically. So time will be 2 pi by omega. So time period will increase. Not much, but maybe few seconds or something. I'm not sure how true is this, but I read an article somewhere like during the time when the dinosaurs were living on the Earth, the Earth used to rotate around 3 to 4 times faster. That means during that time the day is only like 6 hours. Mean 3 hours day, 3 hours night, 3 hours day, 3 hours night. It's just used to fluctuate quite fast. And it's almost 65 million years, right? So from then till now, the Earth slowed down considerably, and now it's 24. So yeah, so if you actually go back to the dinosaurs time, it's every 3 hours there's a day and night shift. Given this, so I can ask you one more like this. If you take a boiled egg, if there is some Jane here who doesn't know how egg works, I'm sorry, but yeah, let's see. So there was one class I was teaching for a medical student, and I said there is an egg which is rotating. Jane student, and the student was like, "Sir, I don't know how what happens inside an egg. I'm a Jane. I have not seen one." Said like, "Okay, so we can't do anything." So we have a boiled egg and we have a raw egg, and you started spinning them. What happens to omega
सर मतलब
if both are given a spin? You took both the eggs and you spinned them on the table. What happens to their omega? Will it remain constant? Will it increase? Will it remain same? Whatever. You took an egg and let's say you gave some omega. After 1 or 2 seconds, if you observe the egg, will it still go faster or will it go with the same speed or what? Now, you should actually know what happens when you boil an egg. If you don't know that, that's a thing. You'll know now. What is the difference between a boiled egg and a raw egg? In a boiled egg, right? In egg normally there is a yolk, right? The yolk becomes solidified. So there is no place for it to move. Everything is stuck. Right? So the basically the yolk is the densest part in the egg and that does not move. So basically the yolk which is there is the densest part. It's like your earth ka core and the crust. Earth ka core is the densest part made of metal and the crust is actually more lighter. Yolk is the densest and it solidifies. The whole thing solidifies. So nothing moves inside. Therefore, moment of inertia remains same. Therefore, omega remains constant. So if you just take a boiled egg and spin it, it'll just rotate normally. Nothing happens. But when you take a raw egg, this entire thing, right, is filled with a fluid. The moment you start spinning this, because of the density, ever seen a washing machine? When you wash clothes, the clothes go to the edges. This yolk, right, will start going to the edge. The yolk will shift. And all this liquid will become something of this sort. The densest part will go to here. And because of this, yolk goes to the edges. Yolk goes away from axis. I increases. This was a CT question, right? They did ask this, and therefore omega decreases. So this egg will actually start spinning a little slower. Omega decreases. Clear with this. You can actually try this, in your society. If you have that this merry-go-round, नहीं है वो क्या बोलते हैं उसको? They have that spin wheel, no? Remember? You can just spin it. I'm sure if you have one in your society, you can actually try this, huh? You spin this fast, you jump on top of it, you go inside, it goes faster, you come outside, it comes slower. Let me show you how it looks though. But I hope everyone is clear with the egg part. So do remember that, even I know in case you don't like eggs and all, but still, question did come in means CET. Ah, Aditi.
Sir, I'm still kind of confused about the raw egg
क्या
because
हो गया raw egg का?
if we spin the egg, उसके अंदर का जो content है, it would also spin. It's not solidified. So
हाँ,
wouldn't that
agreed.
make the
No, but
omega
it gets
automatically?
displaced, na, see, because this is in a liquid form, it can be pushed to the side. Washing machine mein, when you put clothes, what happens? Initially, you keep the clothes in the center, but once the liquid starts spinning, won't the clothes come to the edge? So there is nothing. They're just simply getting displaced. No, the exchange places. You're getting it. No one is spilling out or no one is going away anywhere. They both are exchanging places. The lighter one will go to the center, and the denser parts will come to the outside edge. So mass is still same, but the distribution becomes different. Making sense?
Yeah, okay, so got it.
So look at this.
This is a demonstration of the conservation of angular momentum. I have a couple of, looks like 5-pound dumbbells in my hands. I've got a platform that spins freely on its axis. I'm going to stand on this platform and then have my able assistant, David, come over and give me a spin. And then what I would like to do then to my,
okay. So the professor is standing on that spin wheel. So he has two dumbbells, right? Now, if he keeps the dumbbells closer to himself, m into r square, r is small, the moment of inertia will be less. When he stretches his hands, he is increasing the distance, m into r square, moment of inertia increases. So by bringing the dumbbells inside and outside, you can change your moment of inertia. Clear? Now see, he kept the hands completely out. So moment of inertia is maximum. Clear? Now his assistant is going to push him, he'll start rotating, and then he keeps the hands inside. Okay, so observe what happens to his speed. So there he's spinning. Now, did you see how fast he's going when he brings the hands closer? Look at this.
You can see my tie flying up. So
did you observe that? Every time he puts the hands away, he goes slower. Brings closer, he goes faster. Look at this again. He spins fast. Slows down.
You can see my tie flying
Spins fast. Slows down.
So ice skaters use this principle.
So they actually use this in ice skating also. When they're spinning, they do the same thing. Let me show you one more. I think this is the ice skating thing, yeah. This is the precision. Look at this thing. If you just keep that, nothing happens, huh? But if you spin this is the gyroscope actually. This is actually the concept of a we'll talk about this also. This one. Yeah, this you can try in your society also. You'll find this thing. There, you spin this. Get under this. Now see, he's standing on the edge, okay? This is rotation. You can observe if he gets closer to the center, can you see it's going faster? This is a rotation B. When he's in the center, it just rotates much faster. Now, but if he goes to the edge, now see what he does, huh? He stretches his body outside. Can you see how slow it became? So by going inside, you're decreasing I, so omega increases. If you come outside, I increases, omega decreases. So you can literally see this happening to you. Huh? You can try this thing if you have one in your society. This is International Space Station, ISS.
Hi, my name is Mike Fossum. I'm the commander of Expedition 29. Welcome to the International Space Station. You may wonder why the International Space Station doesn't tumble in its orbit around the obtains our attitude control system, if you will. There's really two key basic
So
parts.
he's going to show us the angular momentum का thing.
Conservation of angular momentum to compete that
Where?
off switch here, or I'll tie myself. But watch
There,
this.
now
I'm
see.
gonna have to put the microphone, or I'll tie myself up.
There. So he's using himself. He's trying to spin himself. And when he brings his hands closer and hands far, see what happens to his rotation. So there he's spinning himself. He brings the hands close, he goes faster. He slows down. When he stretches the hand, he slows down. When you bring the hands again, he goes faster. When he makes himself straight, he goes even faster.
Again, what's going on?
Did you see that? So I'm going to put all those videos in the group anyways, but this is what I'm saying. This thing, it's a little difficult to visualize, but until you see that. What is this exactly? This is also, these are rotating on a table. You will see this question anyways later on. This is another good one, right? Versatinium.
I am here at the University of Sydney, where the mechanical engineering shop has built this incredible piece of apparatus for me. It is a 40-pound, that is 19-kilogram flywheel on the end of a meter-long shaft. Can you imagine trying to hold this out horizontally with just one hand at this end? It is virtually, it is impossible, okay? Now I'm gonna let...
Now see, what he's doing, right? He made a flywheel. Remember this question? There's a disc rotating with a rod. It's kind of like that actually. So this guy, right? He made a disc with a rod. This whole thing has a weight of roughly 20 kgs. So he brought some strong guy just to show us, that you can't actually lift it that comfortably by catching at one end. So there, look at that.
Go. You gonna be able to hold this at all? I so.
There you're trying to lift it.
Make it horizontal. Hold it. Hold it. Hold it. Come on. Just try to. I want you to hold it out horizontal. See if you can. Hold it. Hold it. Oh, come on. What I'm going to do is I'm going to.
So it is clear, right? It is very difficult to hold it with one hand and trying to keep it horizontally. But if you do something, if you spin that wheel, something happens.
Spin this up to a few thousand RPM. Then I'm going to attempt just that. Hold it from one end and have it out.
Rayan, are you listening? You're doing something else. Yeah, can you please focus on the class? We're not playing some movies here, so you need to listen.
3, 2, 1.
So did you see what he did here? He took that wheel. That's a wheel which is rotating. So they're rotating it to very high speed.
5, 4, 3, 2, 1. When I let go of my
Now see, he's going to leave the hand.
what you'll see is that the shaft remains horizontal.
Now see, he can just hold it aram se.
It almost looks as though the wheel is weightless. How does this work? Well, instead of pulling the wheel down to the ground as you'd expect, the weight of the wheel creates a torque which pushes it around in a circle. You may recognize this as gyroscopic precession. For a more detailed explanation, click the annotation or the link in the description to see my video on the topic. Here, I want to try something more extreme.
I'm going to try to lift it over my head with one hand while it's spinning. Wish me luck.
But before I make the attempt, Rod wisely suggests that I first check if I can lift the wheel above my head without it spinning.
Let's prove that I can lift it just this end without it spinning. Here we go.
So he's catching with one end.
I mean, it's just kind of awkward with the hand. Careful.
That's a 20 kg thing. It's really heavy to lift.
Barely. Oh, goodness. Do you even lift? Clearly, I do not.
Undaunted by my lack of
Now
strength,
you're spinning,
I'm
yeah?
going for it. But I want to make sure that the wheel is spinning as fast as possible to give me the best chance of success.
Give it 10 more seconds. 10, 9, 8, 7, 6, 5, 4,
3, 2, 1, go.
That was perfect. Now I'm going to release my left hand and holding only with my right hand at the end of the shaft, I'll try to lift it up over my head. This is a 40-pound, 19-kilogram flywheel. Ready? Here we go. 3, 2, 1.
You see that?
Beautiful.
In the beginning, you're struggling to lift it, but once it spins, it becomes so easy to just lift it.
Nice. All right. 3, 2, 1. It feels incredibly light as I do that.
You can see how he's lifting with a single hand right there. That too, see, he's not catching the left hand, he's catching that other hand, which was supposed to be the most difficult to do that. If you remember in the beginning, he brought one big, strong gym guy. He couldn't even make it straight. This guy is just lifting it over his head. So, there. So we'll see how that works. Basically, you need to revolve it. That is a catch. If you stop revolving, it will fall down. And if you notice that there are two things happening there, okay? So that wheel, when it is rotating, it has its own angular momentum, L bar, because of this spin, omega. And this whole setup is rotating. We can actually calculate that, but fine. So what is happening here? This is your mg, right? And this mg is creating a torque, which is in this direction. So if you take mg cross r, the torque is in this direction. So there. So we have a torque in this direction. We have an angular momentum L bar out of the plane, and both are perpendicular. So technically speaking, if the rotation was not there, the body would have just rotated normally and would have fallen down. Now, because the torque is perpendicular to L bar, the L bar is rotating in a circle. Did you observe one thing? In all the cases when he is catching, he couldn't keep it at rest. Did you observe? Every time he was catching it, this thing was always rotating in a circle. Did you observe that? Because the moment you stop it from rotating from circle, L bar will not change. If L bar does not change, then torque will make it just fall down. If you notice in that video, right, there was not a single case where he just hold it straight and it didn't move. Every time it was going in a circle. Basically, the L bar will keep rotating. That was the whole catch. The L bar has to keep rotating in a circle. So instead of using mg to make the rod fall down, you're using it to make it go in a circle. Mathematically, it makes sense, but thoda difficult to visualize. And if you see, actually, this problem which I made, right? If you guys remember which one, this question, angular momentum. I was kind of inspired by this problem, this one only. So you can actually try this, and someone want you can try this as a homework problem. So if you assume there's a gravity g here, the question is find relation between omega 1 and omega 2 so that the rod remains horizontal. That would be a pretty good advanced paragraph question. Find omega 1 or omega 2. Find the relation between them so that this entire system, instead of falling down like this, it will rotate in a horizontal circle. You can try that as a homework problem. That's a little bit about it. Now, if you see that video, right, you can do some pretty crazy things. Huh? Imagine you go to a magic show, okay? You have a big dumbbell kind of thing. Remember in old movies they show this, people have this gada, the weapon. Lord Hanuman ka weapon dekha, gada. These things are pretty massive, isn't it? You can't just lift them and start beating people with it. But so what the magic trick, right? Is like this. You call someone onto the stage and you tell them, okay, this is a big gada of 100 kgs, please lift it. And that guy can't lift it. Then you say like, okay, I'm going to do some magic. And maybe let's say inside there is an internal disc. There is a motor connected here and the disc starts rotating internally. You can't see that from outside, but there is something rotating inside. Now, if you try to lift it, you can easily lift it up, isn't it? So for a person outside, it feels like something suddenly happened, but if you know angular momentum, you'll understand. There. So when you take science to the extreme, it looks like magic. Go, take a break. Come back by 9:45. We'll continue from here. We'll do more on this. Angular momentum can be pretty crazy. Like the video which I showed you, right? It is very difficult to visualize like why he could do that, but mathematically you can explain. Chalo, come back in 5 minutes. Any doubts on this? Chalo, come back in 5 minutes. Sure, let's start off. Camps on everyone. Let's see one more. So we got a disk here. Thickness T, mass M, radius R. This is rotating with omega. Then what you did, you took another disk, not identical. You took another disk whose thickness is same thickness T, right? And the radius is R by 2. Same material. And you placed on top of it. Find new omega. Let's get this. Others do keep your cams on. Right, Samyak. Right, Arya. Same story again. So when you keep the disk on top of it, due to internal forces, right? The friction is internal. So conservation of angular momentum, I1 omega 1 is equal to I2 omega 2. So what is the initial moment of inertia? It's a disk mr square by 2 omega is equal to, what is this moment of inertia? Mr square by 2. The common mistake is this. If the radius is r by 2, mass becomes m by 4. Right? Because what is mass? Density pi r square into thickness. So this will be rho pi r square by 4 into thickness. So mass is actually m by 4. So this will be mr square by 2 for the big disk, m by 4, r by 2 whole square by 2. This is for the small disk into omega. You get omega nu will be 16 by 17 omega. Check. So when you put one more disk on top of it, you just have to add the moment of inertia. I1 omega 1 is equal to I1 plus I2 omega dash. All clear with this? Vedika, clear with this? Utsa? Clear with this, Utsa? Rudransh? Advay? Any doubts on this? This is a pretty good one. Huh? Most people go for that. They think mass of the disk is m by 2. Be careful, it depends on area. Next one. We have a cone, a truncated cone, a part of it. This radius is r. This radius is 3r. you have a particle of mass m, you projected with speed u, right? And gravity is there, and this height is h. You observe this particle, right? Because of velocity, it will try to go, but because of gravity, you will start going down also. You start spiraling like this. So find the minimum speed so that the particle does not come out from the bottom side. So here, this is an open thing. There's an open here. There is nothing there. Find u minimum. If the particle does not come out from the lower opening. You're getting what is happening? Actually, so this thing, you know how it will go? Just to give an idea what is happening, I'll tell you. See, it is a fight between two things. It is a fight between your centrifugal force, which is pulling it out, and mg, which is pulling it down. So initially, your speed is u, right? So because of gravity, you start going down, but as you go down, your speed increases. As you go faster and faster, the centrifugal force becomes greater than mg. Once centrifugal force becomes greater than mg, you start slowing down, and then you start going up again. Then again you go to the top, and now mg becomes greater than centrifugal force because your speed decreases. Again you come down. You're getting this motion will never stop. It comes down, then it goes up. Then comes down, goes up, comes down, goes up. It just keeps going up and down. It is stuck between these two up and the lower openings. Because if you come down, your speed increases. If your speed increases, centrifugal force increases, so it will pull you up. Right? And if you go up, your speed decreases. I hope you're getting the process, what is happening. Now, how to do this? So find the speed required. So there's a minimum speed. If you don't give enough speed, you're going to come out. Find the u minimum so that it does not come out from the lower opening. I hope the picture is clear and you got what is happening. Try. I'll give 2 minutes. So what's happening? How do you think? Remember the process. What did I ask you? Find the speed, it should not come out. Again, look at the words. Huh? You're not bothered what is happening in the model. You're only bothered about you should not come out from the final thing. So simple, right? This is based on conservation. You have three conservations: linear momentum, energy, angular momentum. See which one works. Even though everything I explained with forces, you can't actually use forces to solve. You. Let's see. Without H, someone got an answer. How is that possible, right? So, what is your initial state and the final state? Your initial state is the topmost point. This is the final thing. So here you are going with speed u, mass m. Here, when it is coming out, this can have a speed Vx and Vy. I could ask that also. Matlab, if the speed is u, with what speed it will come out? So this will actually try to come out at an angle. Since you're asking for minimum speed, Vy must be 0. Since it doesn't come out, for u minimum, Vy must be 0. Great. This height is h. Since the whole thing is smooth, this is smooth. There is no friction, so work done by external force is 0. This is your state 1 and this is your state 2. Energy in state 1 is equal to energy in state 2. Initial energy half mu square, potential energy mgh is equal to half m vx square because Vy is 0. Next thing. Now, if you take the axis about this thing, torque about this axis is 0. Now, if I ask you this question, is the torque on the particle 0 about that axis? About this particular axis 0. There is a torque, but it's not about this axis. Therefore, angular momentum about this particular axis is constant. What is the initial angular momentum? M, u, radius is 3r. What is the final angular momentum? M, Vx, r. So Vx is equal to 3u. Take this and substitute here. That will be half mu square plus mgh, half mv 9u square. That will be 9 minus 1. That will be 4mu square. So u square is equal to u is equal to root gh by 4. Check. Clear, Samir? Where are you? See, the R shouldn't come in the picture anywhere. Any doubts on this? So one energy conservation and one angular momentum conservation, and you're done. Shane, clear with this? Any doubts on this? So the question looks complex, like, you should know like what is happening, but after that it is easy to solve. Let's see one more. Top view. We have a spring fixed at one point. The spring constant is K and the natural length is L. At the end of the spring, you kept a particle here, mass M, and this is given speed U at an angle theta. So this whole thing is placed on a smooth floor. So on a smooth floor, you took a spring. One side you fixed it on the floor. Another side you kept a particle M. Actually, I can give like this also. Let's say this is U and this is theta. And when you kicked it with speed V, find the maximum elongation. and maximum compression, I can find both. So one end of a spring is fixed on a smooth floor. And the other end is attached to a mass m as shown. It is given speed u and theta. Find the maximum elongation. Just write the equation. Simplification is a little messed up. Find max elongation and compression. There is no gravity, Matlab, it is on a smooth floor, so gravity is not there. Gravity is acting in and out of the plane, so we don't require that. I hope the picture is clear. Let's give it a try. Just get the equation. Solving this is a mess. You don't have too many variables are there. नहीं हो गया इतना अच्छा तो नहीं आएगा. Why do you think I'm telling you just create the equation? I know what you did. You thought only this component is responsible for elongation, na? But think about this. You say sine theta. After some time, spring will become like this. Then this component is not u cos theta anymore. It is something else now. You getting it?
Sir,
So it
I'm
doesn't work
having a
that
very
way.
bad answer. Like, how can I type it?
You're sleeping in the class. That's the problem. अभी तक मैं क्या बोल रहा था? Last 2 minutes I'm saying, boss, just get the equation and leave it. You can't solve it. It is very messed up.
No,
So
sir,
leave
my
it. When I
equation
show
is
you,
also
you
so
can
bad
verify.
I can't write. Like, I can't type that equation and it's that bad I'm getting.
ठीक है शौर्य. Once I do it, you can verify whether you got it right. मैं वही बोल रहा हूँ. Don't type it. You can't type that thing करके. You're not well क्या? Tired.
Yeah, sir, like, not been well for like today. Like,
लग रहा है. चलो, no problem. Let's see what to do. I'll tell you one thing, again, not a concept, but a general observation, okay? Remember this thing. In 11th and 12th, at least, right? Anytime you see a particle not moving in a circle or a straight line, other than these two, if you are going in any weird path, there is only one way to do. Conservation of angular momentum, conservation of energy. Remember this thing. If you're not going in a circle or if you're not going in a straight line, right? You can go in some weird path, you can go in an ellipse, you can go in hyperbola. Generally, one of the most common thing to do is angular momentum conservation, energy conservation. Clear? So keep that in mind because this sentence which I told you, right, will keep coming multiple times. In gravitation, it comes a lot. So now coming back to the question, let's see the picture. Now we can play more theoretical things. So let's try to figure it out. One thing is clear, okay? It's based on conservations. So eventually, this is length L. At some point, the spring will stretch. This will become L plus X. Can someone tell me how will the velocity be at this instant? The velocity must be perpendicular to the spring. Any idea why? If the velocity is not perpendicular to the spring, so that is the first thing you need to check. At max elongation or compression, you cannot have a velocity along the spring. Because if you have a velocity along the spring, means what? Spring will still stretch, na? Are you getting the point? So at max elongation or compression, the component of velocity along the spring is zero. It is not rest. Huh? There will be a tangential component. There can be a radial component. That is the first thing you should know. Without that, you can't go ahead. So at max elongation or compression, the component of velocity along the spring must be zero. And let x be the elongation. Great. So it's clear. It gives you a feeling we have to use conservation. There's no force. Second thing, can I conserve linear momentum? Can I conserve linear momentum? Yes or no? No. Why? Can I conserve linear momentum? Yes or no? No, but why? To conserve linear momentum, what should happen? No, spring force is internal, no, Samyak? My system is spring and the particle. Spring force is internal. Remember, this point is fixed to the ground. So there's a force on the ground, na? Since that O is fixed, it is attached to the ground, there's a normal reaction there. Yeah, there's an external force on point O. Since O is fixed, there is an external force. That's the reason that point O is not moving, or else the O would have gone from there. Therefore, linear momentum is not conserved. There, one conservation is gone. Can I conserve energy? If there's an external force on the system, can I conserve energy? But there's an external force, no? Work done by external force is zero. Why? Displacement is zero. Since O is fixed, it is not moving. So you have force, but you don't have displacement. Remember work done ka definition? Force into displacement of point of application of force. So therefore, energy is conserved. Can I conserve angular momentum? Torque about the point O is zero. Why? Since spring force passes through that. The forces will always pass through O, so torque is zero. Therefore, L bar is conserved. I hope you're getting how you're playing. This is what I was saying. You should actually check every time which one is conserved. There, it is clear. So I can conserve energy and angular momentum. You're done. So initial angular momentum is equal to final angular momentum. Initial angular momentum, remember mv perpendicular into L. So this component will be u sine theta. This component will be u cos theta. So this is m u sine theta into L. That's your initial angular momentum is equal to m v dash L plus x. Energy conservation. Energy in state 1 is equal to energy in state 2. Initial energy half mu square. Spring is in natural length. Spring energy half kx square and the kinetic energy half mv dash square. So get v dash from here and substitute here. You'll actually get a quadratic equation. You'll get two roots, x1 and x2. One is maximum elongation, one is maximum compression. You can leave it here. If you got the two equations, you're done. Numbers are given, you could have solved it. Is this clear, everyone? All clear with this? Let's see one more. Last one. I'll do an easy one. Let's say we have a disk. Mass and radius are hinged at the center. So a bullet of mass small m goes with speed u, hits it tangentially and gets stuck. So top view will look like this. The bullet of mass m comes with speed u and gets stuck. This is an easy one. Find the omega of the disk after collision. Hits the disk tangentially and gets stuck. Find omega after collision. Standard question. Same story again. You just want omega final, so I have to conserve something. Same story. Can I conserve linear momentum? You can't. Why? You hinged in the center, so that's the external force. Can I conserve energy? No. Why? The bullet is getting stuck. Means E is equal to 0. It's an inelastic collision. So what's left? Angular momentum. Are you getting how to think? I have to conserve, and there are only three things. You need to check for each and every case. So let's see the picture there. So this is the picture before collision. After collision, the bullet gets stuck here, and this whole setup is rotating with omega. Torque about the hinge is 0. Therefore, L initial is equal to L final. So initially only the bullet is going, so the angular momentum is MUR. This is for bullet. Disk is at rest. Then when it gets stuck, the total moment of inertia will be mr square by 2 for the disk plus small mr square for the bullet. You can treat the bullet like a particle into omega. This is moment of inertia of the disk, and this is the moment of inertia of the bullet. There, you get omega from here. Easy? Clear, na, Sudiksha? Devanshi? Rudransh? Clear? Shreyansh? Clear, na, Shreyansh? Next thing. Same thing, a similar one. We have a disk, mass m, radius r. We have a person standing on the edge of the disk, and this guy jumps with u relative to the platform. Hope you guys remember this thing. We did in momentum questions. So man jumps tangentially with speed u relative to the platform. Find omega of the disk after he jumps. Mass of the man is small m. Finish off. Last one for the day. Let's see. You actually get the same answer. So see. So initially the person is standing here, everything is at rest. So L initial is 0. Now after he jumps, the disk is going with omega. So this point here is going with the speed of r omega. Now remember, when you say you're jumping with speed u relative, the moment you try to jump, your legs are already going back with r omega. So you're actually going forward with u minus r omega. Do you guys remember this? We did this thing in the momentum problems. Not jumping with u, you're jumping with u minus r omega. So your L final must be, for the man ka angular momentum, m into u minus r omega into r minus k cap. And for the disk, it will be mr square by 2 omega. There. This is for the man, and that is for the disk. Since angular momentum is conserved, L initial is equal to L final. You solve this, you end up with MUR is equal to MR square plus MR square by 2 omega. You get similar answer. All clear with this? Yeah, I think most of you got the same. So be careful with that. You relate to think it's the same concept which we did in the moment of the chapter. Okay, with that we will wrap up for the day. So next class when we catch up, we'll continue from here. We will do more problems. I think mostly next week we'll wrap up the chapter. Next class we can wrap up most of it. It might spill over a bit. But next Thursday, we will wrap up the chapter. And after this, we'll start off with fluid mechanics. That'll be the next chapter. So, okay, this week there's no test. The new test will be online tomorrow afternoon. So, yeah, any doubts, anything else, please stay back and ask, or else you're free to leave. I'll see you on Tuesday, same time. So, take care, stay safe.